So let's go ahead and get started. Hello, everyone, and welcome to the Aether Community Meeting. Thanks for joining us. This meeting, by the way, is being recorded and will be made available afterwards. So everyone that's registered will be able to get the video. All participants have been placed on mute for the duration of the video. If you'd like to ask a question, please use the chat module at the bottom of the screen. And then following the presentation from the folks from Purdue, we'll have a Q&A session and try to get to all of your questions. So I'm pleased to introduce the team from Purdue that will be discussing their 5G Lab to Life platform initiative and some of the research they're doing, and quite a bit of that is using Aether. And so, excuse me, just to make clear, it's not the chat button at the bottom, it's the Q&A button that you're going to want to use. So I'd like to welcome Mohammed Chabas, Charlie Hugh, David Broker, and Troy Hagee from Purdue. Chabas and Charlie I've known for a long time. Chabas is the Kevin and Susan Kahn New Frontiers Assistant Professor in Computer Science, and Charlie is the Michael and Catherine Brick Professor of Electrical Computer Engineering, and he heads up the Distributed Systems and Networking Lab at Purdue. So they've been doing research and networking, and now a lot in the wireless space for quite some time. David and Troy are with the Purdue Research Foundation, which is where a lot of the collaboration activity happens between the Purdue researchers and the corporate world and the rest of the world. David is the Chief Innovation and Collaboration Officer, and Troy is the Vice President of Innovation and Technology in the Purdue Research Foundation. So they've got an exciting initiative they're going to tell you about. Before I turn it over to Chabas, being an alum of Purdue, I just wanted to mention that if you hadn't taken note, Purdue's new president is Meng Chang, who is a researcher in wireless communication. He used to be a collaborator of mine, a colleague of mine at Princeton, was then Dean of Engineering at Purdue, and is now the president of Purdue. So you can rest assured that the work that's going on here is very much front and center in the kinds of activities that are going on at Purdue. So with that, let me turn it over to Chabas, and we'll get started with the presentation.
All right. Thank you so much, Larry, for the introduction. So hi, everyone. My name is Chabas, and today we are going to talk about the various sort of things that are happening at Purdue University. So I think ONF Community Meeting is like a very interesting platform where we can actually bring in the things that are not seen by the outside world on activities and stuff that are going inside Purdue. So we're taking this sort of initiative and using this venue to sort of bring to your attention things that have been taking place on various fronts inside Purdue, and I hope you will like it as we discuss them through this talk. So let's just move on. So basically Purdue, again, I'm a new professor at Purdue, so I just started here. I myself didn't know all the various things that were going on at Purdue before joining Purdue. But once I joined Purdue, I found there are a lot of sort of diverse initiatives that are happening and taking place in here. Sort of from the wireless space, what's going on is Purdue is sort of a place, is coming out to be a place where you can start building, start doing wireless research from the ground up. There are a lot of infrastructure that is being built up. There's a lot of research that is going on, and the kind of talent that you need is all sitting within a sort of a university footprint that can work together and do some amazing work. So for example, on the research and development side, we have a lot of work going on in the mobile space for traffic analysis, modeling, and generation. And there's a lot of amazing faculty like Charlie, who is here with us, then Chunui Pang, Saurabh Bakshi, and also our president, Meng Chang. They're all doing some amazing work in this space. Similarly, it's not just about analysis and modeling of 5G. We're also working on building system designs. Again, we know Aether is one example. There's a lot of other work that is going on in sort of designing, characterizing, and optimizing these new platforms that are coming up. So we have faculty like Sonia Fahmy, Christopher Brinton at both Purdue CS and ECE, which are working together in sort of building these next generation platforms for 5G and 6G. So this is again from the research side only, but we also, the nice thing about Purdue is it's not just about research. We also have real developments going on as part of Purdue through our Purdue Research Foundation that Troy and David will talk about, and also these testbed that we are building at Purdue. So one of the work, for example, we are doing is building this 5G edge cloud sort of presenting Purdue as a edge cloud where multiple tenants can come in and run their sort of workloads, mobile cores, and so forth. So for example, two such examples are ONF Pronto edge site that we are working on. So setting up a new site as part of the Pronto project that was DARPA funded and is sort of led by ONF and other sort of institutes. And now Purdue is joining in as a new site in that environment. And so the idea there is to take that workload, run it on our edge cloud and sort of enable a new site for that nationwide testing that is going on. Similarly, we are doing this other project that is sort of NSF 5G convergence edge site. So this is basically a NSF funded project where we are focusing on doing full stack research all the way from the UEs to the RANs to the base stations and then into the mobile core to be able to do things like enabling high security, better performance, and so forth. And the interesting thing is, on the same 5G edge cloud that we have at Purdue, this is going to be running as another workload on that environment. And I'll again discuss more about it in the later on slides as they come up. And lastly, we have this Purdue Lab to Life 6G and 5G R&D infrastructure, which is like an actual sort of like a mini smart city that is being built at Purdue. And then I'll let Troy and David sort of talk more about it as we move on. So in this talk, the idea is we will give you a glimpse of all these 4 elements that I talked about, things that are happening on traffic analysis and generation, things that we are doing on system design and optimization for these next generation systems, and then a brief overview of this edge cloud and the Lab to Life 6G infrastructure that we have today. So for the first one, I will hand it over to Charlie, who's going to talk about the recent work we have done on modeling the control plane traffic in these MCN networks. Over to you, Charlie.
Great, thanks, Shabazz. So I will take a slightly deeper dive, I guess, into this project we've been doing recently on trying to model the control plane traffic of mobile networks. And the motivation for doing that is really straightforward. Yeah, give me a second. There is maybe this is latency. I apologize for that. So 5G. In the past few years, 5G deployment has really taken off, and major mobile operators reported 100x increase of control traffic volume. So this is really made the performance of the control plane of mobile core network to become more important than ever before. Now, to perform any kind of performance study of, say, control plane architecture design requires a traffic generator that is accurate. It can generate a realistic control plane traffic from UEs, and that is also scalable with any given UE population. And that's also versatile. For example, you may want to generate traffic for a particular device type or for a particular time of the day, and also for a particular subset of control, say, events. Now, the major finding from this study is the Poisson process or Poisson distribution that has been commonly or widely used previously to model internet data traffic cannot accurately model or capture the inter-arrival time and the sojourn time for the control events in the mobile core network. So in particular, our contribution is we developed a 2-level hierarchical state machine-based traffic model that can accurately capture the traffic diversity among the UEs, as well as the dependence among the control events generated by a particular UE. And this traffic generator will be made available in the near future as part of the Aether Community Meeting. So next few minutes, I'm going to go into a bit of detail about this major finding and also give you some intuition about how our model works. So again, to start with, we really try to understand whether the Poisson process, the Poisson distribution, can capture the control plane traffic in the mobile networks. If we could, then we will have a very easy time to build the traffic generator. Right? So the goal here, just to make it very specific, we're trying to basically model the interval time, a certain time of control events generated by each UE. So we're not modeling the aggregate control events by a bunch of UEs is not enough, because to benchmark, for example, mobile core design or an implementation, we really need a per UE, a realistic traffic per UE, because the mobile core needs to maintain per UE state. So the standard, we do have in the 12 box, two standard Poisson distribution fitting tests. They're called KS tests and AD test, the standard test for testing the Poisson distributions. So what we did is we acquired a week-long raw trace from one of our mobile operator partners at their MMEs that consists of about 40,000 UEs. The control events, all the control events for 40,000 UEs. So we started by just trying to fit the control event traffic for this each single UE, whether you can fit with a Poisson distribution. Quickly we found out the per UE traffic varies significantly throughout the time of the day, so on an hourly basis, and also can differ and can vary significantly for different device types. So basically, based on the MEI tag, we could classify the devices in the trace into three types: phones, connected cars, and IoT devices. So this really suggests, well, basically, so following this, we basically partitioned the trace by basically extracting the interval time, sojourn time for each UE for each so-called event type, hour, device type tuple, right? And then try to fit this, perform these two tests of Poisson distribution. And but when we do this, we found out we simply don't have enough data to model to perform this test. Basically, we end up with like less than 10 events per UE. So what we ended up doing is to aggregate this per UE inter-arrival sojourn time for, again, each event type, our device type tuple, but for all 40,000 UEs. So this will give us enough data to perform the two tests. So what we found out, 0% of all these tuples, event type, our device tuples, the traces for those tuples could pass these two tests. We actually did one more thing. We basically tried to apply k-mean clustering to cluster this 40,000 UEs into so-called similar groups based on two metrics, based on the number of events per UE and the variance of interval time per UE. Right, so this gave us a few dozen groups. So the UEs within each group would have somewhat similar behavior according to these two metrics. Then we reperform these two tests, statistical tests on this the trace for each group, again for all the tuples, and we find still less than 5% of the traces for across all the tuples could pass the test. So the takeaway here is we really tried really hard, trying to kind of refining our tests by slicing and dicing the raw traces and trying to really hoping to that Poisson distribution could fit capture the control plane traffic in the mobile network. But our conclusion is it is not working. Poisson distribution simply will not do the job. Now, for people who are working in this kind of traffic analysis and modeling, probably you are wondering, what's the fundamental reason for why? So we did do a couple of a deeper analysis, but in the interest of time, I won't be able to go into the details. So I'm just going to leave these two slides. We can certainly discuss offline or during the Q&A. So given the Poisson distribution could not capture this control plane traffic in the mobile network, how can we then model the control plane traffic in order to develop a realistic traffic generator? So observe there are really two limitations actually to this Poisson models. Number one, as I just showed you, they could not actually fit this per event type, the basic traffic for each event type for even a set of similar UEs. Number two, even if they could capture the distribution of per event type, they cannot model the dependence among different events. As we all know, the control events generated by UE have interdependence. So our approach is to start with a finite state machine to model the event dependence. So the 3GPP specified the EMM and the ECM state machine, so which could be combined into this three-state state machine as seen shown in the bottom. which also shows the transitions, shows essentially the fault control events that basically causes the state transition. So this is not enough. So this does not capture the remaining events. So what we ended up doing is to refine the two lower states with additional substates and finite state machines to capture the remaining events. So then we go back to the trace, we'll model the probability for each state transition and distribution of sojourn time staying in each state. And we do this for the typo here, for each hour and the device type tuple. Essentially, basically, we essentially trying to customize the model for each hour and device type. So this would give us essentially the model for each hour and device type tuple. Then we do this for all the hours, 24 hours in each day, and for all the device types. So let's quickly look at the accuracy of our control traffic model. So essentially, we compare our new model and also, as well as a baseline model that simply basically use the best fitted Poisson distribution by given a raw trace. And in generating traffic for 380,000 UEs for about a 1 hour window. So basically, we acquired again the raw trace from the mobile operator that will serve as the ground truth. So the first figure you'll see here essentially compares the breakdown of the events, right, of all the control events. For the raw trace, for the trace generated by the base model, and for the model generated for the trace generated by our model. Right? What you see here is the breakdown of the trace generated by our model almost identical to the breakdown of the events generated by the raw trace, or in the raw trace. So furthermore, we compare the distribution of number of events and the sojourn time staying in each of the states by each UE across all the UEs. So this would give us a CDF right, across all the UEs, right? For each of the three traffic trace, right? So then how do you compare basically this CDF? Essentially, we calculate the max Y distance between pairwise CDFs. So the smaller the distance, the more similar the two CDFs. So what you see here is the red, which is basically max Y distance between the CDFs of real trace and CDF of the metrics for the trace generated by us. It's significantly smaller than the maximal Y distance between the CDF of the real trace and the CDF of the trace generated by the baseline model for the two metrics. So with all those results, we basically conclude that our model really can generate pretty realistic traffic for any given UE population. So I'll stop here. I'll pass it back to Shabazz.
All right, thanks, Charlie. So yeah, so the thing is, like, again, as I mentioned in the early introductory slide, there are like 4 different things that we are doing in terms of research. We are focusing on modeling the mobile traffic and also building systems for them. The reason why we ended up like there's a lot of work that is being done, especially in modeling the mobile traffic, is we know that next generation systems are coming up. There has been a lot of focus on the data plane traffic in these mobile core systems, which again, we have very good models for them to sort of regress them and test them. But control plane is becoming the next frontier in these mobile cores. How do you model them? How do you scale them? Or how do you design systems for them that meet the latency requirements that are being placed on them with new use cases? So for example, we know that in the 5G space, the expectation from the next G mobile cores is pretty daunting, right? Like, we want it to be able to run massive Internet of Things with like sort of very low latencies and like very large scale. Similarly, we have these like mission critical applications that needs to provide higher availability running 24/7, and then also again be able to run at very fine grained latencies, and again also in the presence of high mobility. So similarly, the third case again is the enhanced mobile broadband. And I know as a networking community that is working in the mobile space, we know that these are the use cases that are coming up with 5G and next G. The question is, how do you tackle them? And so far, I would say the community has focused heavily on, which is the right direction, on the data plane and making the data plane faster, be able to like process things very, very fast. but control plane is also like the key critical component in them. Like whenever you're doing mobility, handover is coming in, right? IoT devices, in order to maintain battery, they're going up and down all the time to conserve battery and so forth. So we cannot simply ignore the control plane component. And also, as I will mention later on, the drive towards from like this monolithic design of mobile cores to a more disaggregated design is also placing a lot of pressure on the control plane in order to provide lower latency and higher availability. So let me say, what is the expectation then? What is the expectation from these cores? Is, in my understanding, there are these three things. They have to be performant, be able to meet the throughput and latency constraints. They have to be scalable so that they can support the large number of users as well as the devices that are coming up, like the IoT devices, self-driving cars, and so forth. And second, in order to enable those two, what we have found and what has what the community is now focusing on is like these systems have to be scalable so that we can easily modify them and upgrade them to sort of support all the new use cases that we have been talking about. So what has been like, what did we have before? So in the 4G space, we know that we have this EPC core that has these sort of these relatively fixed function monolithic designs that were there to sort of enable 4G, enable the innovation, the applications that we had at that time. But again, if you look at across these three metrics, we can say that they were performant given the use cases that they were working on, but they were not scalable and they were clearly not flexible. So what happened with 5G and NextG then? We said, okay, let's change the whole paradigm into a more microservice-based cloud-native design where the control plane has been split into its minute components, where there is an AMF, an SMF, and these databases. All of these are communicating, running as functions, like microservice functions, and communicating with each other over a shared bus. And still, the data plane component is still running either as a software, like based on DPDK or running on Intel servers, or it's running on these new architectures that we have, like Tofino switches and so forth. But again, the key part is data plane is still there. We have architectures for accelerating the data plane. The thing that has changed radically from 4G to 5G is not the data plane. It's primarily the control plane, which is now a more microservice-based architecture. So now if we look at the sort of the three metrics again, what we are finding out is performance is actually getting hurt a little bit because we have jumped from a pure monolithic design to an extreme microservice-based design. Again, yes, it's all software-based. It's really like it's scalable, it's disaggregated, it's flexible, but now there is an impact on performance that we have to sort of handle. And clearly in our evaluations using Aether, we have found that yes, there's work that is needed now in improving the sort of the performance of these control plane components of these next mobile cores that we are developing. So again, we are flexible. Again, in terms of scalability, I would say they are scalable in the context of like adding new functions because they are software, but in terms of performance, they are not there yet. And again, I'm not talking about the data plane performance. We're doing pretty good on the data plane part. It's the control plane performance that we see is getting hurt in this new paradigm. So here's like an example like of the sort of the evaluations we did. And we found like, so let me first explain this plot. So this plot is telling you how does the latency of a specific control plane event varies as we add more and more UEs on a mobile core, like onto a mobile core. So in this case, we were using Aether and we were using a service request event to find out, okay, how the latency varies. And you can see the desired latency that the community is sort of focusing on is 10 millisecond. The preferred one is around 20 millisecond, but they still desire to have a 10 millisecond latency for these systems on the control plane side. So for a single UE, clearly Aether is able to cope up. We are getting the latency within that sort of time frame. But as we start increasing more and more UEs, the latency sort of radically increases in these systems. Now, why is that happening? Like we have moved from a monolithic design to a disaggregated design. Why is it that the system is not coping up? So what we again see in this case is like when we do a deeper performance analysis, the insights that we get from our analysis is that the common sort of notion is we can just add more servers and CPUs to get higher performance. But we are seeing that adding more CPU and memories does not actually help here because the existing CPU and memory that we already had in those servers were not being fully utilized. There's ample resources that were available there. The main bottlenecks that we found out are basically the serialization and deserialization that is happening between the events that are coming in from the RAN that you need to serialize and deserialize using the NGAP protocol. Similarly, you saw that there is an SBI bus, a service bus, that is connecting all these functions together. So something that was previously accessible as a function now in the same process is now you need to issue a RPC to get that sort of service from another function in that microservice architecture. So that is actually adding further latency into the design. The other interesting thing that we found is Aether and other mobile cores that we are developing today are based on Golang, which is clearly the right direction to go. It's a concurrent it's a concurrent language that allows you to have these very lightweight threads that you can spin up and down. But the thing is, these Golang schedulers have been developed for running cloud native applications on public cloud, like at the end of the sort of where the actual bigger services like Netflix and other stuff is running. They're not designed for running these very latency critical applications that are emerging. Like, so for example, 5G is emerging as a cloud native workload. That workload has clearly different latency and throughput requirements than some other workload that is servicing machine learning or video or something else. So the scheduler has to take that into account, because what we are seeing is the default scheduling policies that we have in that scheduler are actually also hurting the performance of these 5G workloads. And similarly, there are other contentions that are happening on the locks and channels that are there in this mobile core design that we have. But so these are the main points that are hurting the performance of mobile core. So again, the idea is like, what is the way forward then? Like how we go about optimizing them. So what we have found, again, we are working very closely with ONF and Intel Labs and Aether folks on sort of looking at Aether and trying to sort of come up with different ways of optimizing them. So one way is like what we found is Aether, the default Aether design that we have today is based on single instance stateful service functions. So each function is basically a stateful function that is doing everything. All the state is local to that function, and it processes everything, and then it moves on. So in order to scale, we know that in these cloud native architectures, scaling these stateful functions is very hard. We have to design them if we are designing them using actual cloud native principles, then the function has to be stateless, and the state has to be stored in somewhere in some centralized storage that you access using RPCs. So this is something that we have done recently with ONF in converting this initial implementation into a multi-instance stateful service functions. The second thing that we can do is, again, disaggregation is necessary. Horizontal scaling is necessary, but we also have to focus on latency, right? Like, what is the latency that we need to get? So I think one thing which is counterintuitive here is like we still need vertical scaling in some sense. And what I mean by that is we need to sort of capitalize on these new emerging hardware that we have, like SmartNICs, programmable data planes, to help accelerate the sort of performance of these control plane events. And we cannot just rely on CPU in that case. So we need to sort of do some kind of vertical scaling through by accelerating these sort of events using these emerging architectures. And then again, I mentioned that we need to sort of think about different ways of scheduling these sort of Golang services, these functions. The scheduler has to be designed keeping in mind that it's sort of handling these very low latency, very sort of high throughput functions that are coming in. It's a workload that is different from any other workload that is servicing other applications like machine learning and stuff. So we believe that these are the ways to go forward, and there are many others that we haven't explored yet, but we have started making some baby steps in that direction. So let me just give you an idea of like what how does the performance of a single instance Aether changes versus the multi-instance Aether that we developed. So what we have done, again, a lot of kudos goes to ONF engineers, and especially Ajay, who has been working very closely with us and with one of my students in developing these new multi-instance stateless 5G core architectures. So what we have so far in Aether was an AMF function, an SMF function, UPF, and all these other functions connected over a SBI bus in a cloud native architecture. But today, this AMF was just a single instance, a stateful instance, and scaling it was very hard. So that's why we see that as we increase the number of UEs, the performance was going sort of degrading with the increase in the number of UEs, because they're getting delayed in the queue for this function and so forth. So what we have done is basically converted that AMF into sort of this multi sort of function design, where there is a load balancer for SCTP sitting in the front. Then we have different instances of AMF, And you can now scale them horizontally as many you want. And these are stateless functions. And the state is now being stored in MongoDB, where you do this RPC request to get the information. So again, we just did this for this one at SMF. We believe that as other functions start becoming bottleneck, we need to scale them up this way as well. So let me just show you like some sort of evaluation we did between this single instance versus multi-instance Ether. So we are calling single instance one Ether, and we are calling Ether plus the multi-instance function that we have. So if you see, the blue line is telling us about the Ether, the basic, the vanilla Ether that we have. And then we added 2 more functions of AMF, 2 more functions of SMF, and like what if we run 2 more functions of SMF and AMF together? So if you see this plot, again, we have latency and number of UEs on the x-axis and latency on the y-axis. For a single UE, Ether is with a stateful function is performing really well. But as you start increasing the number of UEs, you will see that the latency of Ether, the vanilla Ether, is starting to increase rapidly. But for 2AMF, for this service request event, as we go on, in the beginning, yes, Ether, vanilla Ether is performing well, but at some point around 20 UEs, you will see that the multi-AMF, like the one with 2AMF, is starting to perform better than the vanilla design. And again, I want to point out, like we were also scaling SMF in this case, and you can see SMF is still performing pretty badly compared to vanilla Ethernet. And the reason there being is we have different kinds of events coming in 5G. For example, we have service request, we have handovers, we have registration, deregistration. So each of these different functions that we have in the mobile core become bottleneck for each of these different events. So for the service request, AMF is the bottleneck, not SMF. So that's why scaling AMF is necessary if you want to sort of handle large number of UEs coming in with the service request. Similarly, for other functions that we are evaluating, and we are actually working on a full paper on this with more details, we see that other functions become bottleneck. So recently, like there's a lot of work done by the community in sort of coming up with new designs for mobile core, where some designs have said, like, why not we put all these functions in one server, and then as we need more, as we increase the number of UEs, we run new instances of these servers. The thing is, like, again, as we are seeing in this particular case, it's not that the full core is becoming the bottleneck. Individual functions are becoming bottleneck, so they have to be scaled accordingly with respect to the load that is coming in. So hopefully we'll share more details as we go on working in this space. But this is what I wanted to share so far, the work that we have done in the system space. And again, thank you so much to ONF and their team in working with us and in building this system. So from here, I'm actually going to so I'm going to like now jump onto the development work that we are doing in Purdue. So the first thing that I will quickly go over is like this 5G edge cloud that we are developing at Purdue. So for this one, it's a very simple and basic design, but the key things that we are doing in there is we know that 5G is running as a cloud native workload. And wherever we have a Kubernetes cluster, we can launch this workload. But the edge cloud is different than the workload that is running on it. So the first thing, if you want to do or enable research in this space, is you want to have a edge cloud running in your like sort of institution so that you can run these cloud native workloads on them. 5G being one of them, AR, VR, machine learning, and these other workloads can become other workloads that can run on this cloud. So for this one, we are following the sort of the initial design that ONF Ether has proposed. We have a rack of servers connected over a pair of Tofino switches. But the interesting thing here is like it's a full end-to-end stack. Like we have base stations connecting to Tofino, going all the way into the edge cloud and on to the internet, accessing internet or other functions that are out there. So in this one, the other interesting thing is we are following the exact like cloud principle. So we are using this open source tool called Proxmox that allows us to build a mini sort of cloud-like environment in here. So we can spin our own, it's a hypervisor with the ability to spin our own VMs, our own containers, and sort of implement these zones, security zones, like one use case running in its own zone, which is isolated from the other one, another one. So here, for example, right now we have 3 zones that we have, we are sort of, 2 of them are already there, and one of them we are working with Purdue Research Foundation in running it on this one. So it's basically the idea of a zone is that this is a secure enclave. Once you're running your workload in here, you're basically a tenant running on this workload, and that tenant is sort of distinguished from the other tenant. So zone 1 is one tenant, zone 2 is the other tenant, zone 3 is the other tenant, and so forth. And all of them are running their own cloud native workloads, 5G being one of them. So this is what we have. And the nice thing here is, like, unlike running on a public cloud provider, here, having this full stack access, we can do innovation on all layers. We can go deeper into the provider space and do modifications there. For example, changing the scheduling policies and so forth. We can even go into the tenant and change sort of scheduling policies and workloads and all these things in the tenant space. So having that capability allows us to sort of tweak all these different layers of the architecture. And so just based on time, so I'll just quickly move on. So for example, in the NSF 5G convergence use case or zone, what we are doing is we are working with other universities and we are opening up this sort of a VPN connection to our edge cloud where their base stations, for example, a software-defined radio is going to connect, and then they can do RAN-based evaluations and UE-based evaluations over there. So this is pretty exciting because now we are getting like full stack, like full end-to-end access on this environment. So with that, I'm going to stop here and I'm going to hand it over to Troy to talk about our 5G 6G lab to life R&D infrastructure.
Thank you, Shabazz. Yeah, so kind of picking up from the conversation on some of the research activity that's occurring at Purdue University, at this point of the conversation or discussion, we're going to pivot a little bit and talk about some of the really the idea of the lab to life platform that we've been building at Purdue University. And the idea of the lab to life platform is that it's really built on this idea of kind of three pillars. The idea of networks and architecture and a lot of the stuff that Charlie and Shabazz have been talking about. It's built on the research and scientific expertise of the university. And then it's this idea kind of matched with that of test beds and real world use cases. So the idea of the lab to life platform is really trying to bring these three kind of pillars together in a way that we can really advance research and sort of a real world environment, and largely in collaboration with various other partners, both academic and commercial. So in the idea of the lab to life platform, one of the things that we're looking at are the various different test beds that we can substantiate at Purdue University. And so as we were looking across both the campus and a lot of our research centers, and then even at Discovery Park District, which is it's a 400-acre real world kind of environment. People are living, working, kind of playing there. It's a residential community, single family homes, multifamily housing projects, as well as retail right on the edge of Purdue University. That's really where we got started. But then in addition to the Discovery Park District, which is kind of our smart city environment, we're also looking at test bed deployments and capabilities along State Street, which is kind of this main road that separates the Purdue University campus from the Discovery Park District. And in that corridor or test bed, we're looking at automation, mobility, additional smart city applications, traffic applications. We're looking at a test bed deployment at the Purdue University Airport, again, looking at mobility, but this time looking more at aviation and drone activity. We're also looking at test beds at the, it's called INMAC, but it's the Indiana Next Generation Manufacturing Competitiveness Center. They have a facility there in which they're able to model manufacturing, advanced manufacturing environments with robotics and automation, and thinking about the different ways in which connectivity and wireless connectivity can advance that space or sector. And then we're also doing some projects or looking to do some projects and network deployments at our agronomy center, which again is part of the university, the ag department at the university, but looking at applications for wireless technology in agriculture. And then the last test bed that we're really looking at is at, it's a little farther west of campus, but it's the Wright Forestry Center. And it's really in that area that we're looking to build a UAV outdoor range, test range, with a focus really towards unmanned traffic management and air traffic management and unmanned traffic management for drone activity. So in all of these test beds, what we're really trying to provide is a step in between science and research occurring in the lab, and then real world sort of at scale environments where that science can be applied and use cases can be developed and validated and optimized before broad scale commercialization. So in many cases, that may not be required or useful, but as we're engaging with corporate partners, there is a lot of interest in these types of test beds to both kind of match the technology, but also optimizing that for specific use cases. And so this is the idea of the test beds that we're trying to curate around the Purdue University campus. Matching those test beds then, as many of you know, Purdue University is a land-grant university. The enrollment's about 50,000. It's very strong in STEM. As President Mung Chiang likes to say, our engineering program is ranked 4th nationally, but we graduate as many engineering students as the other 3 combined. So sort of quality at scale is where Purdue kind of positions itself. Very strong, again, in electrical and computer engineering, computer science, and then a bunch of the related centers and research programs that we have that involve numerous faculty across the university. So that's sort of on the academic expertise. And then on the third piece of the puzzle is the network activity. And so in really creating these test beds, it's about the various use case applications. So manufacturing, transportation, aviation, agriculture, but really building those test beds with connectivity and network deployments that support the kind of research and application development that we're trying to foster. So where we started with this was building a neutral host platform. So it's a common shared fiber and edge data center network that supports the Discovery Park District. So again, that's about 400 acres, a couple of industrial sites, housing, retail, residential, commercial office building. And then in addition to that, we've also deployed in the Discovery Park District a CBRS LTE network. It is a Solona network, core and RAN, and it's operated commercially by a company called SBA Communications. And through our partnership with SBA Communications, we've got access to that network for application development, as well as research deployments, testing, optimization, validation projects. In addition to that, we've struck a deal, but we're currently deploying an Ericsson-based network. Again, it's a CBRS 5G network, private network out at the Purdue University Airport. That network should be operational by this summer, probably in a couple of months. And again, for the Discovery Park District network with SBA Communications, and then also the airport network with Ericsson, we do have access to both GAA, but also PAL channels. We've acquired the rights to be able to use some PAL channels. So again, it gives us additional flexibility to leverage those networks for different types of projects. In addition to that, we're in the middle of discussions and conversations with several partners about opportunities to expand our asset base on the network side, looking both at licensed spectrum with commercial carriers to come in and support 5G deployment at INMAC, which is the manufacturing center. We're in conversations with some companies about an open architecture private network at the agronomy center. Again, looking at later this year, having the technology stack sort of agreed to and being able to work on deployment. We're working on a millimeter wave deployment along State Street, and we're evaluating options in 28 gigahertz, 39 gigahertz, and 60 gigahertz in terms of exactly what bandwidths we're going to use for that network. And then the last one is that we are looking at an open architecture private network, again, at the Forestry Center to support some of the drone and UAV management applications that we're looking to put out there. Again, the first 3, the deployed and the deploying, those are real and the partners are identified and we're moving forward. The first one, the network's already operational. The second one we're deploying right now. And then the other 4 on this list are conversations that are ongoing. And at this point, I would like to point out that we are actively looking for additional partners, both on the academic side and commercial side, that can really work with us to kind of think about, what do these technology stacks look like? Are there partners that can provide and collaborate with us, can co-invest in these deployments as they move forward? And then the last part of this, based on these three pillars, what the university is really looking to do is to leverage kind of this idea of the lab to life platform, which again is this idea of the scientific excellence of the university with real world at scale test beds, with network deployments, to leverage opportunities to pursue grants. This is just an example, but several here span infrastructure grants as well as research grants, leveraging and co-investing around the idea of the lab to life platform and some of the network deployments that we're looking to put forward. And with that, thank you. I'll turn this back over to Larry.
So I think, yeah, thank you for the presentations. And I think we're now ready to do a little Q&A. And I've got a couple of questions of my own, but let me get to the ones that the audience has entered in. This is primarily, first one is about the latency and performance analysis slides that you talked about, and wondering if there are some other low latency middleware technologies that you've considered. You talked about Golang, but maybe low latency Cobra based middleware, or are there alternatives that you've looked at?
So far we have focused on what open source community has done for us, like Free 5GC and then Aether, and so our focus has primarily been on those ones, and we are focused, like we were looking for 5G compliant cores, right? There are definitely other options available, but when you're talking about cloud native architectures and the paradigms that are there for implementing those applications, we have looked into those so far. So again, it's a very nascent work. We will definitely thinking of looking into these other options. And again, if you have more suggestions, please reach out to us, and then we'll be happy to sort of work with you.
Okay, so I've got one of my own to stick in here since it's on the topic of scale, which is making the AMF stateless. At first blush, it looks pretty stateful. That your any given microservice or container is processing a particular stream's set of data. So what I suspect that means is that the AMF is shrunk to sort of a template of an AMF, and you have to go to MongoDB to get the state that you wanted. That's going to push. Tell me if I got this right. That's going to push the bottleneck onto Mongo, I would think. And
Yes.
that fetch.
Yes.
Okay.
So the thing is, like, if you look at today's cloud native designs, where they're talking about the functions that are doing the actual operation are stateless, but the state is being maintained in these backend as a service. So they are not function as a service. So they're BaaS in some sense. And the idea is the BaaS are being actually implemented as very highly available beefy systems, right? So they should be able to handle these large number of functional requests that are coming in. So even if you today look at Amazon S3 and all these things, they're actually providing that storage to you as a service. And then they're saying your function can interact with them, store them, and be able to get certain level of performance guarantees when they're interacting with them. So you're not building the backend as a service as a traditional function as a service, right? Like they're saying functions are stateless, but the other part is mostly stateful, built using C++ or whatever the mechanisms you have to build high performance systems.
Okay, thanks.
Yeah.
Well, I'm going to follow that thread one more time because a question just popped in, which is now you started talking about Amazon, and so you've sort of taken the edge cloud that you talked about, and now you've gone back to the hyperscalers. How do you see functionality moving? What lives where?
So the thing is, the reason I brought up Amazon is I'm talking about the services that they're giving. I'm talking mostly about the cloud native design as to when you're talking about building a cloud native application, there are stateless functions, there is storage. How do you implement the storage? Storage has to be very sort of highly available, very powerful in some sense, and functions are basically stateless talking to it. I gave an Amazon S3 or S3 example because that's what we have so far today. Whether there is a edge version of it today, I don't know. So that's why the open source community, we are using MongoDB and all these other functions in today's age. But if we want to make them production ready, we need to replace them with something similar to what Amazon has on the cloud front.
Okay, thanks. All right, so I'm gonna shift to Charlie a little bit, and so your work on the modeling of arrival times of the UE traffic. That's some great stuff, but you're making it available then in the GBSIM package. I was just wondering if you could talk generally about where that package stands today and how it, where it might go. Is that what the future of it is? It seems like it could be a pretty important, especially when you look at this from an open source perspective. The open source / research community having access to a pretty powerful simulator seems like a very important thing. Just if you could talk a little bit about that.
And certainly, probably it's better. I can pass this question over to Shabazz, so you are more familiar with the status on the Aether implementation.
So I think I can start with the Aether part, and then maybe in general, like why is there a need for such a model? Maybe Charlie can then come on and talk about it. So from the Aether development part, what we are doing is with GNodeB Sim today. Again, you can either have a actual base station talking over SCTP to this mobile core. The nice thing about the Aether platform and with GNodeB Sim sort of functions running in front of it is like the core is still real. Like you are using a simulator like GNodeB Sim in front of it, but the core itself does not make any distinction between them. So with using GNodeB Sim, what we are doing is you do micro benchmarks today. You have them, you can run them, like you can say, I want to run this event and this event and this event. The challenge there is like, how do you convert that into a real trace? So what we have done with Ajay at ONF is like, we are now making it more parameterizable. So rather than when you run an event and then go to the next one, instead of having a fixed second, like, okay, 1 second and then go on to the next one, you now pick from a real trace. There's a distribution that you get, and then you sample from that distribution before going to the next event. So it's not open, like this particular part is not open source yet, but we do have a private repository that we are working on. Now, what Charlie is working on is like working on providing that distribution for the functions that we need to feed into the system. So this is where the Charlie's work is sort of coming in.
Or the model that generates the realistic distribution. That's right.
Yeah. So let me try to connect a few dots here because we've got a live lab. Are you making traces available, or is that how would you make such data available so that people like Charlie could build on it and refine his models?
So maybe let me expand. So basically, just to point out, like our interaction with Purdue Research Foundation have recently started. Like the deployments are happening there. So the current work that Charlie is doing is with a large service provider. We don't want to like sort of name it, but again, we are working with the actual large service providers to get us those traces. We cannot share those traces as is. But again, if we can sort of convert them into this sort of anonymous distribution, like this is the time distribution that you have. Those distributions, I think we should be able to make them open source. But yes, once we start doing the actual deployment in Purdue Research Foundation, I think those traces we might be able to actually provide them as raw data that you can then use.
So yeah, sort of in that sense, just to turn to David and Troy for a minute in terms of the interactions with the researchers. This seems like access to data is king. Do you have experience with that? Is that something that's happening in certain settings? I know you were bringing in some incumbent vendors. Is that, I heard Ericsson, I forget who else.
Yeah, so on the vendor side, what we're largely looking for is realize that the idea of the test beds is really sort of an applied approach, right? It's kind of this intersection of industry and research and science. And so it's in that intersection that when we start engaging these companies, what they're oftentimes really focused on is, their commercial products and how to improve their commercial products. And what they're very interested in is the use cases, right? And so by having these test beds that really facilitate work in different use case domains like manufacturing or agriculture, aviation, automation, the companies have a lot of interest in that. And so what we've been able to cultivate with them is some partnerships where they're co-investing or donating technology that's allowing us to substantiate these networks. And so a little bit to your comment about, as we operate these networks, some of the networks PRF will probably operate ourselves. They're private networks. They're pretty limited applications, like at the Ag Center, for example. We can operate that network, and as an operator of that network, we have sort of ownership and control over the data that's flowing over that network, and the applications that write on that network, and the applications that are generating the data and everything. And so that gives us, additional, as you're commenting on, additional capabilities and assets that can be leveraged by the faculty and that can be shared out by other collaborators and partners. Now, in some of the cases, a couple of the networks, and actually the very first network we deployed was a partnership with SBA Communications. And, they're trying to commercialize applications on that network. It's a commercial network. So they're making the network available to us. And for applications and use cases that we're deploying on that network, we have a lot of control and leverage and flexibility with, but we don't have the ability to sort of leverage data that's going across that network that's more as part of a commercial client contract, right?
So if I could say that back to you, when you're the operator, you get to decide who you collaborate with on the use of that data. And
that's right.
In certain settings, you brought the vendors in, but you're the operator. That's great. So as an operator, just to push that in a direction that's near to my heart, but maybe a little scary for you, which is, what about operating a network that's built on something like Aether or an open source? Maybe you don't know enough details about it, but is that a possibility instead of a proprietary solution?
Yeah, absolutely. And in my one slide, I may have gone over it pretty quickly, but I think some of the network deployments that we're looking, part of the test bed is that we want to have different networks with different features and different characteristics so that we have a broad set of assets that can be used depending on what the project is and the project requirements are. And so we are purposely deploying multiple networks, not just sort of one monolithic network across all these sites. And so at each site, there's kind of a separate network that's getting deployed. And at a couple of the sites, we are very much looking at networks that would be based on an open architecture platform. And so in those sites, we could envision actually working very much with some type of Aether deployment as part of that deployment, as we're sort of sorting through the partners and the technology stack and how we'd actually substantiate.
So you have some of the spectrum that you not only the relatively unlicensed, but you've acquired rights to some of the CBRS spectrum.
Yeah, the primary spectrum that we're working in right now with our existing networks is CBRS. And we have, as you know, there's some auction sold by county. We have sublicensed the rights to some PAL channels within Tippecanoe County, which is where Purdue is located. So if we have a project where the project or the project sponsor is nervous about using GAA, we can access the PAL channels and run the project on PAL. And then, of course, if we're partnering on a particular deployment with a commercial carrier, like T-Mobile or AT&T or Verizon, we can partner with them to access their licensed spectrum. So it just depends kind of on how the partnerships are coming together for any specific deployment. Interesting.
So again, connecting the dot, I've got a grid on my screen, so I'm connecting you with Shabazz here for just a second. You have an edge cluster where you talked about multiple zones. Is a zone is that like, it's a multi-tenant cluster, is that right? And so you've got a cluster you've got a tenant that's the Aether tenant, but you got another tenant that's someone else.
Right.
So someone was asking.
Not a slice. So I saw the question. So it's not a slice we are talking about. It's like it's a tenant, and in that tenant you can run your Aether core, and that Aether core can have multiple slices for whatever use case they have. Yeah.
So the other sort of big point here that comes across to me is the commercial people are, of course, very interested in the applications. They know how to do networking. They're just the applications. Within Purdue, there's research going on. Certainly, there are people with applications, but there's also people down in the middle of the network. So it'll be interesting, kind of just tying all the pieces together here, and maybe because we're at the top of the hour. It's always been a challenge to find the right way for networking researchers to participate in these sorts of things. And it sounds very promising. So I'll just give you a chance to closing thoughts, and then
I think I will let Troy talk about it, because there's a lot of different areas like agriculture, construction, and all these going on. So maybe Troy can sort of.
Yeah, just given that we're at the top of the hour, I'll make this brief. But Larry, to kind of respond to your question, I think what we're really trying to curate, because you're exactly right, what we're really trying to curate is an environment that's really supportive of corporate partners coming in and working more collaboratively with our academic faculty. And it's really about creating opportunities for those interactions to occur, to build relationships that then can spawn, research collaborations and deeper level of engagement. And so part of the test bed is trying to just present opportunities that companies are interested in engaging in, and then working with faculty to kind of figure out what those projects might actually look like. And so in some projects, we're working directly with commercial R&D folks. And in some projects, we're working specifically with Purdue University faculty. And then in some projects, we can envision kind of those two groups coming together and really collaborating as a team around a particular project. And so part of the idea of the test beds is just creating the environment that really facilitates this type of engagement occurring in some form.
And the only thing I'd add, Troy, is the focus is obviously on developing technology, but there's all kinds of other things that has to come together, like business models and things like that. So we really do try to take an integrated approach when we pursue these projects.
Yeah. So again, we are close to the end. So just as a closing remark, I think it's sort of like an invitation to the community itself to come in and sort of participate with us. There's a lot happening across the entire stack, from the UEs to the RANs to the mobile core to the use cases, and we have the necessary infrastructure. It would be nice to have people both from industry working with us, investing in this with us, and also from the research academic side to participate with us. There's already some participations going on, but I think this is a very nice sort of environment, where a lot can happen across all these different layers we have. And this is an exciting time to be in this space.
It absolutely is. So thanks to all of you, and we will wrap it up here. Thanks, everybody.
Thank you. Thank you, everyone. Thank you for the opportunity. Bye.